Everyone for inviting me here and for coming to this talk. So I've been interested for a few years now in conformal inference, which some of you may be familiar with already, but it's a pretty broad term now for describing statistical methods for estimating predictive uncertainty using machine learning algorithms. So very broadly speaking, the type of problems that one can solve using conformal prediction can be sketched like this. So there's a data set that has been labeled a supervised data set. There is some type of sophisticated machine learning algorithm that produces a predictive model. And then we're interested in using this predictive model to make predictions or assign labels for new objects. And here in this cartoon, we are imagining that there's some sort of binary classification problem where we have blue documents and red documents, and we would like to build a classifier that can tell us what is the correct color for a new document. So this is a pretty rough schematic of a lot of machine learning problems. And conformal prediction is particularly interested in quantifying in a precise way the uncertainty that we should have in the predictions calculated by the machine learning model. And the key aspect of this type of research is that it tries not to make any assumptions about how the machine learning model works. So that the same types of statistical methods can be used with different models that could be very complicated. So today I will talk about some applications that use deep neural networks, but really nothing that I'm doing is specifically designed to work with deep neural networks. You could easily apply it instead to do predictive uncertainty estimation for random forest or any other type of machine learning model. And you can even start to think about how to use similar techniques for even more complicated machine learning models like generative neural networks and so on. So the reason why I find this area of research interesting is that as we all know, machine learning algorithms are being used everywhere, and it's a very rapidly evolving field. But at the same time, despite all the success stories, people are increasingly aware of the limitations of trusting algorithms, and the stakes of many of these applications are increasing. As people rely more and more on machine learning algorithms for all sorts of things, from medical diagnostics to self-driving cars, the risks associated with making mistakes increase. And so I think one key component of trying to increase the reliability of these systems and their social acceptance is to provide some sort of confidence measures associated with the output of these models. And this is something that conformal prediction can help with. So what makes conformal prediction a very powerful framework and an increasingly popular one, there are a lot of people who are working on this, and ever more and more people joining this field every year, is that conformal prediction is very flexible in that it can work with any machine learning model. Typically just treats the model as a black box. On top of that, it can also easily work with many different types of data because it doesn't require you to make any modeling assumptions about the data. It will just assume that there's some sort of exchangeability or IID property that your data satisfy, but it doesn't really matter what their distribution is. And despite taking this very agnostic view of both the model and the data, it can provide precise statistical inferences. And the way that it typically quantifies uncertainty is by constructing prediction sets. So it's not necessarily the only way that you can use conformal prediction, but it's an easy one to explain and it's quite useful. So if you're trying to do classification or regression, you know that you can have a model that makes a point prediction, or you can construct a prediction interval or a prediction set. So conformal prediction focuses on making prediction sets or intervals and calibrating them in such a way that you can guarantee some coverage property for those prediction intervals or sets. And so this framework makes conformal prediction quite attractive to practitioners and particularly attractive to me as a statistician because it is practical, it is principled, it gives you precise finite sample inferences, and I think most importantly, it is likely to be durable. Machine learning is evolving very rapidly, And a model that is popular now might become obsolete very soon. Because conformal prediction doesn't really require any assumptions about how the machine learning model works, I think it is likely to stay around for a little bit. So I've worked on various types of problems associated with conformal prediction, looking at different types of machine learning tasks, classification, regression, novelty detection, and so on. There are many other tasks that you can address using conformal prediction, even though I didn't work on them myself. Some of this work was published in the machine learning literature. Some of this work is more statistical. So today I want to focus on one recent work that is a little more statistical and focuses on classification. And the type of question that we're looking at in this project is what happens when you want to do classification, but there is something wrong with your data. And something that could happen with your data is that sometimes the labels that you observe are not the correct labels. So imagine that you're trying to solve this classification task, an image recognition task, and your data set consists of images like this. You may notice that the images have low resolution, they're a bit blurred. That doesn't matter. The main message here is that sometimes the label is incorrect. So for the images at the bottom here, for example, for this image here, the bottom center, it should be a deer. It kind of looks a little bit like a deer, even though it's blurred. But in fact, in the data set that we observe, this image has been labeled as a dog. So imagine that you have a data set with labels like this. And I'm interested in studying in how the presence of these sometimes incorrect labels affect the way that we do conformal prediction. Now, the reason why we're interested in this type of question is that data sets with incorrectly labeled data are actually quite common. Nowadays, companies and researchers, they often have access to extremely large data sets, but they're not always high quality data sets. And part of the reason for that is that it's relatively easy to acquire unlabeled data, but it's time consuming and resource intensive to label them. It usually requires some people, or often experts, to manually go through each data point and assign a label. One way that people are, one approach that people are taking to address this issue is by outsourcing the labeling. For example, using the Amazon Mechanical Turk, which will hire people to label images manually, and you can have multiple people label the same image so that you can screen out some errors that way. But the problem is that these type of approaches are known to lead to imperfect labels. There are also other applications that I will not focus so much on today, but are relevant, where the labels are deliberately sometimes wrong to preserve the user's privacy. So there is already quite a bit of literature in machine learning on learning and fitting models with noisy labels. So I will talk about these imperfect labels as being noisy labels sometimes. However, not as much work has gone into studying how to estimate predictive uncertainty when you have noisy labels. And so because conformal prediction typically looks at the model as a black box, I'm going to assume now throughout this talk that the model has already been trained and maybe was trained on noisy data, on data with noisy labels. But now we're interested in constructing prediction sets using conformal prediction. And so I want to study what happens when you use conformal prediction with data with noisy labels. So there is some very recent work that started to look at this problem and concluded that quite often conformal predictions tend to be conservative in the sense that they produce prediction sets or intervals that are too wide. Here's an example of a numerical experiment that I ran that is consistent with our findings. So here, for example, I'm fitting a neural network to predict the labels of some images in a 10-class classification problem. And I'm varying the number of data points used to calibrate these prediction sets. And on the left-hand side, you see the average coverage over multiple experiments of these prediction sets. Nominally, they should have 90% coverage, but in practice, they have coverage closer to 93%. And on the right-hand side, you see the average size of these prediction sets. So ideally, we would like these sets to be as small as possible, of size close to 1, because in a classification setting, a prediction set of size 1 is the most informative prediction set you can have. And so here we're seeing that these prediction sets are a little larger than they should be, which is consistent with their findings. So the focus of this project I'm going to present today is to study more precisely this phenomenon and quantify in an actionable manner how large these prediction sets are and then develop a solution so that we can construct prediction sets that can adapt to the presence of label noise and eventually achieve the coverage level that we would like to achieve and be no larger than they need to be. And here you can see a preview of how that method will work on this image classification dataset. So when the sample size is small, it will not be able to improve much, but as long as the sample size is large enough, it'll be able to remove the extra conservativeness that comes from the presence of those noisy labels and give us more informative prediction sets. And before we get into the details of how this works, I want to emphasize that this is not an easy problem at all. In fact, if you just look at it and you don't assume anything more, I will introduce some assumptions, but if you don't assume anything more and you just say, okay, so we have some data with the wrong label, and now I want to predict the true label for a new test point, it doesn't mean much. Like, how is that possible? If the noisy labels are chosen in a completely adversarial way, then there's no way. How can you predict what the true label is? You've never seen a true label. So there's not much meaning in this question. It's an extremely challenging question, but we will see that we can make a lot of progress by assuming just a little bit more about how these noisy labels are being assigned. Okay, so they need to be assigned at random in some way. Okay, so before I present any novel results, I need to give you some background on how conformal prediction methods work. And so I will try to give a background that is as concise and general as possible. So this may not be all exactly the same way that it is presented in the literature, but it tries to summarize different approaches in a unified view. So the standard setup that you typically have in conformal prediction in the classification setting is that you have data that consists of pairs. There's a variable X that contains the features of the data points. For example, it could be an image. And then you have a label Y that can take capital K possible values. You observe n of these data points, and then you also observe a new image. And you like to predict the missing label of the new image. The key assumption is that all the n+1 data points were sampled IID from some distribution that can be completely arbitrary and is generally unknown. Sometimes it is sufficient to assume that the data are exchangeable. In this talk, at some point, I will need to assume that they're also independent. So I'm going to start from the beginning and assume that they are all IID. The typical goal is to construct a prediction set for the label of a new test point, which should be a function of the data that you observed up to time n and of the features of the new data point. This prediction set should satisfy some form of coverage, and the typical notion of coverage that people focus on is marginal coverage. Marginal coverage means that this prediction set at level alpha should be such that the probability that the label of the test point is contained in the prediction set is at least 1 minus alpha. And you can think of a typical value of alpha as being 0.1, so you have 90% coverage. Now, this form of coverage is called marginal because everything in these parentheses is random. The test point, both the features and the label of the test point are random. They're random samples from this population P. And the function that calculates the prediction set is also random because it depends on the training data that are random. Standard techniques usually allow you to construct these prediction sets and also to ensure that they're not much larger than necessary. And so under some mild additional technical assumptions, you can show that standard methods give you prediction sets that have marginal coverage very close to 1 minus alpha, as long as the sample size is large. Of course, this is not the only type of coverage guarantee that you might be interested in. There are other techniques. In fact, the techniques I will talk about today are mostly focused on achieving this slightly stronger notion of coverage that is separate coverage for each possible label. And it's called label conditional coverage. So at high level, the simplest implementation of conformal prediction, which is what I will focus on today, is based on data splitting. You have a labeled data set of images, for example, each with their own label. You randomly split it in, let's say, half, but it doesn't need to be half. And then the first half is used for training, which means that you fit some kind of machine learning classifier, for example, a deep neural network on it. And then you apply the deep neural network or your favorite classifier to the remaining half of the data, making predictions for those data points as if you didn't know the true label. And then you compare your predictions to the true label, which you do have, and you evaluate some sort of residuals, And by looking at the distribution of these residuals, you will calibrate a rule that constructs the prediction sets. Once the rule is calibrated, and I will say in a moment what it means to calibrate it, you will apply the same model to a new test point, of which you only know the features. And then you will apply the same rule for constructing the prediction set, and that will give you a prediction set with the desired coverage product. So how does this calibration work? Well, the first step is to extract the relevant information from the neural network. And here, without much loss of generality, I'm going to assume that the neural network provides you with an estimate of the conditional probability of every possible class given the observed features. If you're working with a neural network, this is typically just the last layer of the neural network, which involves a softmax layer. And so that gives you a number between 0 and 1, and is standardized so that the sum of those numbers for all possible labels is 1. So here I'm showing a sketch of a neural network for binary classification that has 2 outputs. So in general, if we do k-class classification, we would have a neural network with k outputs. And these outputs give you these probabilities, these estimated probabilities that I call pi k hat. They're a function of the observed features, and they don't need to be accurate. They're just numbers between 0 and 1. People in computer science may call them probabilities, but as statisticians, we don't need to think of them as being probabilities in any kind of, they don't need to be consistent with the model that is generating the data. They just need to be a number between 0 and 1. Right? But we're going to interpret them as probabilities in a certain sense, but without trusting that too much. So they may or may not be accurate, but the point is that we take them as the key ingredient for constructing prediction sets. So the idea is that we will construct prediction sets by including all labels whose estimated probabilities are sufficiently high. This is a very intuitive approach, and in the simplest implementation, we compare each estimated probability to a fixed threshold. So we have this vector of k possible thresholds. They're not necessarily the same, but they may sometimes be the same. And then we include the label k in the prediction set if and only if its estimated probability is greater than 1 minus tau k. Tau k is this threshold. It's not the only possible approach. In fact, it's not the best approach, but it is the simplest one to explain. In particular, one limitation of this approach is that it doesn't account for heteroscedasticity. So if you think that some images are easier to classify than others, you should actually construct the prediction sets in a slightly different way. In general, we're going to think about this function C that constructs the prediction sets as a general set value function that takes as input the features of the image, passes them through the deep neural network in some way, compares the estimated probabilities produced by the neural network to a vector of k possible, of k thresholds, tau. And then it returns a set in such a way that this set is increasing with respect to each element of tau. And if you set tau equal 1 for any particular component, you can be sure that the associated label will be contained in the prediction set. So you can see that the example I wrote above satisfies this rule, and the more sophisticated example that I was mentioning to, which is what we use in practice in this project, also satisfies this property, but it's a little longer to write explicitly, so I'm not writing it. But I will work with this general approach for constructing prediction sets. So you see this function is a function of this vector of thresholds tau, and tau is what we need to calibrate. Okay, so conformal prediction will give you data-dependent value of tau that guarantees this procedure constructs prediction sets with the guaranteed coverage product. So the way you calculate tau is by first evaluating some residuals on the calibration data. Those are the holdout data points that are labeled but are not used during training. So these conformity scores are generalized residuals, and they're supposed to basically tell you how far away the observed value is from what the model predicts. So one way of defining these residuals would be by taking the difference between 1 and the estimated probability for that particular label. So we're going to define this function S hat as a function of the image, the feature with features X, and a placeholder label K. And it could be 1 minus pi hat K, for example. In general, this conformity score function is determined by the function that we use to construct the prediction sets, and it's basically inverting that function. So from now on, I will talk about this conformity score function as being this function written down here. So it's the smallest value of tau indexed by the label k, such that the label k is contained in the prediction set. And this thing is a little bit more difficult to write for other choices of rules for constructing prediction sets, but it has this nice form for the simple rule that we saw before. Okay, so now we need to evaluate these residuals on all the holdout calibration sets, calibration data points. And then what we're going to do is that we're going to split those data points based on the correct label. So this procedure I'm describing here is designed to construct prediction sets with label conditional coverage. This is the stronger form of coverage, and I will focus on this because it's easier to write down all the steps. But in the paper, you can find the details about how you calibrate the thresholds tau for marginal coverage. So for label conditional coverage, you split the calibration data based on the observed label. And we're going to say that we have nk observations with label k, and we put all the observations with label k in this into this set d tau k. Then you evaluate this function using the label k for all the data points whose true label is k. You sort them, and then you calculate the empirical quantile. So you sort them from the smallest to the largest, and then you start counting from the smallest, 1, 2, 3, until you reach 1 plus nk times 1 minus alpha. So this would be roughly the 90th quantile, empirical quantile of these conformity scores, if you're interested in 90% coverage. And we're going to assign this empirical quantile to tau k. So tau k, this is how we calibrate tau k. It's going to be this empirical quantile of these conformity scores. And then you apply the prediction rule that we saw before using this data-dependent threshold tau. And this guarantees you label conditional coverage at level 1 minus alpha. So this is the standard procedure, and it's been implemented using different choices of conformity scores, but it can always be described by this general recipe. Now, everything until now assumed that we observed the true labels. From now on, I'm going to start discussing what happens when you have data with imperfectly assigned labels. Okay, so what is the setup here? So we're going to assume that now we have IID observations, each consisting of a triplet. There's the features X, then there's the true label, that is the label we're interested in predicting Y, and then there's a noisy label Y tilde that is not necessarily equal to Y. Now, the goal is to predict the true label for a new test point, having only observed the noisy labels for the previous n data points. Now, before presenting in new algorithms, I'm going to study what happens when you apply the standard conformal inference procedures that I described before in this setup, using Y tilde instead of Y to construct the prediction sets, but then measuring the coverage of the prediction sets based on whether they cover the true label, the red label. So you see that this in general is going to depend on the relationship between the true labels and the noisy labels. So there's not much you can say in an adversarial setting, but you can quantify this as a function of the discrepancy between the true labels and the noisy labels. And we'll see that we can do this in a useful way. So the first result is that you can quantify this deviation from the 1 minus alpha coverage that we expect in terms of some random variable delta k. Okay, so delta k is a function, and it's a function that depends. It's a function that depends on the calibrated threshold tau k that was chosen by the algorithm that I described earlier. So the coverage, the label conditional coverage, will be 1 minus alpha plus the expected value of this random variable. And there's both an upper bound and a lower bound. So what this is telling you is that the coverage will be very close to this 1 minus alpha plus the expected value. Now, what is this function delta k? It's a function of the discrepancy in the cumulative distribution functions of the conformity scores, conditional on the value of a true label or conditional on the value of a label, of a noisy label. So let me introduce this notation. So f underscore L k, so this thing down here, this is the cumulative distribution function of the conformity scores evaluated for label k, sk, xk, s hat xk. conditional on the label y being equal to L. So you see that this depends on two indices, K and L, and it's a CDF where what is random is the random features X of a data point we've labeled L. The tilde version of this is the same thing, but you condition on the noisy label instead of the true label. And then delta is just the difference in these two CDFs. So if y is always equal to y tilde, this difference is always 0, and the result tells you that the coverage, that conformal inference has 1 minus alpha coverage. But in general, when you use conformal inference with when you use noisy labels with conformal inference, you will have this deviation from coverage. And right now, we don't really know what this value is going to be, this delta, but you can see that it can be either positive or negative. So that tells you that in general, conformal inference may be either overly conservative or overly liberal when you calibrate it using the wrong labels, which makes sense. Now, can we go any further? At first sight, this seems difficult because this quantity delta that we call the coverage inflation factor, this function, depends on two things. One is a cumulative distribution function conditional on the noisy labels, which is something that we can observe and estimate because we have plenty of data with noisy labels. We can evaluate their conformity scores, and we can estimate this green part, we can estimate it. The problem is that we don't have any relevant data to estimate the red cumulative distribution function because we have never observed any data with their true label. So we're going to need to make some assumption in order to try to estimate this quantity. And the first assumption we're going to make that is very useful is that the noisy label is conditionally independent of the features given the true label. This is a very common assumption in the literature on label noise. It sometimes makes sense. For example, if you are working with randomly perturbed labels that were assigned to preserve user privacy, so the algorithms that people actually use in practice satisfy this property. There are other cases in which this property might not be exactly true, but it is very useful. It's a standard assumption. And we'll see that all the results that we derive using this assumption, they seem empirically quite robust, even to those cases where it might not hold exactly. At least some of those cases that we looked at. And on top of that, if you don't like this assumption, you can just console yourself thinking that this is actually weaker than assuming that the labels, the noisy labels are just consist of some random noise on top of the true label, right? So the noise doesn't need to be independent of the true label. But if it is independent of the true label, then you're completely random noise, which is also a fairly standard assumption, but it's even stronger than this. Okay, so first of all, can we use that result to support the empirical observation that standard conformal predictions are typically overly conservative? So we said this coverage inflation factor can be either positive or negative. When it's positive, conformal inference is too conservative. When it's negative, it's too liberal. So in general, it can go either way. But this result tells us that it often results in overly conservative predictions. So this result says that on top of the IID assumption and the conditional independence assumption for the noise, suppose that the cumulative distribution function of the scores evaluated using the true labels satisfies this inequality. Now, what does this inequality mean? Intuitively means that the trained model, which was most likely trained using noisy labels, tends to assign higher probabilities to the correct labels of a new data point. So even though the classifier was trained using noisy data, it achieves sufficiently high and typically just better than trivial predictive accuracy when predicting the correct labels. Okay, so this is a relatively minor requirement, and oftentimes the noise that we have in the labels is not so bad that we are completely unable to train a meaningful classifier. So this is an assumption that is often satisfied in practice. And then this result tells us that when this is the case, the coverage inflation factor is almost surely positive for any label, which means that the coverage of standard conformal prediction applied to noise labeled to data with noisy labels will tend to be greater or equal than 1 minus alpha, and possibly significantly greater. So this suggests that this gives us more theoretical evidence of the fact that conformal prediction tends to be too conservative when you have noisy labels. And right now this result is presented for conformal inference designed to construct prediction sets with label conditional coverage, but you can derive similar results, and we have them in the paper for marginal coverage. They're just a little longer to present. And so this gives us a theoretical characterization of this empirical phenomenon that we're observing here. Now, the big question is, how can we fix it? And I will now describe a method for constructing conformal prediction sets that, using some modeling assumption about the noise process, can construct prediction sets with tight coverage. So this will be based on this assumption. And the reason why this condition-independent assumption is useful is that it induces a convenient linear relation between the conditional distribution of x given the noisy labels and the conditional distribution of x given the true labels. So I will call the former p tilde, and it depends on the true label. It depends on the noisy label, so it will be p tilde k. And the conditional distribution of x given the true label is k will be pk. So assumption 1 implies that p tilde k is a linear combination of pl for different values of l, where these linear coefficients mkl are basically given by the transition metrics between the noisy labels and the clean labels. So now, for most of the remainder of the talk, we're going to assume that this transition matrix is known. Then the paper places some effort in trying to relax this assumption, but I will only be able to cover that briefly. So for now, I'm going to assume that this transition matrix is known. So we know quite a lot about the process that is generating noisy labels. And on top of assuming that this matrix M is known, we're also going to assume that it is invertible, which can be understood as saying that the noise is not too strong that it hides completely the information about the original labels. So when this matrix M is invertible, we call it inverse B. And the reason why this assumption is extremely useful is that it allows us to write the coverage inflation factor as a function of only f tilde. So remember that this coverage inflation factor was defined as the difference between two CDFs, one of which was conditioned on the true labels that we never observed. Now, because of this linear relation, you can write the coverage inflation factor as a function of only the matrix B, which is soon to be known, and the cumulative distribution function f tilde, which is estimable because it is a function of the machine learning model that we have and of the data with noisy labels. So in particular, because we have a holdout data set with noisy labels, what we can do is that we can divide it based on the noisy label that we observe, and then we can evaluate an empirical estimate for the CDF. And so the most intuitive estimate you can use is just empirical CDF, and we have access to this f hat. And so then you have a plug-in estimate for the coverage inflation factor, and I will call that delta hat k. It's a function, it depends on t. Now, the theory that we saw before tells us that the coverage of conformal inferences will be approximately 1 minus alpha plus the coverage inflation factor evaluated at the calibrated threshold tau. So we don't know what the coverage inflation factor is, but we have a plug-in estimate, so that gives us some idea of what the coverage of our algorithm should be. It should be about 1 minus alpha plus delta hat of tau hat, and we know what tau hat is. So now the intuition will be, if we know this, then maybe instead of using alpha, we should use alpha minus delta hat, so then it cancels, and in the end we get 1 minus alpha coverage. Now, doing that is not completely straightforward. There are two issues. The first one is delta hat is not necessarily the same as delta, it's an estimate. The second issue is that delta hat is a function. We need to evaluate it at the threshold tau hat, which is itself a function of alpha. So if you change alpha, then tau hat changes, which changes the coverage inflation factor that matters for you. We should, again, change the way you choose alpha. So we have a dog that is biting its tail here. So we need to break that dependence. And here is how we can break it. So before I can present, so in order to facilitate the way that I present the algorithm that allows us to make this intuition actionable. So the intuition is, instead of using alpha to calibrate your conformal inferences, use alpha minus, use alpha plus delta, okay, where you use the delta hat. Okay, so this high-level intuition can be formalized into an algorithm, and we can prove the algorithm gives us some nice coverage behavior. But in order to present it, first I need to give you a slightly different perspective on how standard conformal inference works. So I said that the standard way of calibrating the threshold tau hat for standard conformal inference is to calculate an empirical quantile of the conformity scores. Well, one equivalent way of doing that is to write it in this form. So we denote the order statistics of these conformity scores evaluated on the data, on the holdout data points with noisy label equal to k. We call them SK and then in parentheses I. So those will be the order statistics. Now the standard way of setting tau hat is to set tau hat equal to the value of these order statistics indexed by ik hat, where ik hat is the smallest element of this set, script ik, which is the set of indices I between 1 and nk, such that I over nk is greater than 1 minus alpha. So this is almost equivalent to, there's a small factor that is missing, but it's almost equivalent to saying that tau hat k is the 1 minus alpha times 1 plus nk empirical quantile of the conformity scores. Okay, so you can trust me on this one, you can check. The reason why I wrote it like this is that now I have an intuition that tells me that I should replace alpha with alpha plus delta, where delta is my coverage inflation factor. And so now I'm going to modify this algorithm by changing the way that the set script ik is defined. So now I'm going to add this blue term, which is the plug-in estimate of the coverage inflation factor, and it's a function. I'm going to evaluate it at the ith order statistic. And then there's another term that will take care of all the estimation errors that I have and will allow me in the end to write some nice coverage results. So I call this the finest sample correction factor. It's a lowercase delta. It's a function of the sample size, and it's a function of the sample size in a complicated way. So it depends on the number of data points we label k, and it also depends on the number of data points in the smallest class. Now, what's intuition? Intuition is that the capital delta k factor tends to correct the conservativeness of all your inferences to mitigate the unwanted behavior that is being induced by the noisy labels. So if the noisy labels are making standard conformal inferences too conservative, as it is usually the case, the true coverage inflation factor is positive. As long as our plug-in estimate is sufficiently accurate, that means that delta hat k will be positive. And so what we're doing here by adding delta hat to alpha is that we're basically increasing the significance level of our prediction sets. So if you're interested in 90% coverage, instead of using alpha equal 0.1, we're going to use alpha equal 0.1 plus something positive. So it's making our inferences less conservative, which is what we want. Okay? They're too conservative to begin with. This is going to make them a little less conservative. But then we have to make them a little more conservative than that because there are possible estimation errors due to the fact that instead of observing the correct inflation factor, we're estimating it. And that's what this positive lowercase delta is doing. Adding any positive number in this set is going to make the conformal inferences a little more conservative. So now there will be these two competing forces, but the main idea is that the finite sample inflation factor will become increasingly small as the sample size grows. And so this will basically, and at the same time as the sample size grows, the capital delta term, the plug-in estimate for the coverage inflation factor, will become closer and closer to the true coverage inflation factor. And so this will cancel out nicely and we will get tight coverage. And that's what the next result says. Now, before we show you the next result, I can give you the, I can show you that this coverage inflation, sorry, the finite sample factor, it has an explicit form. Okay, it's a bit ugly to write, but the point is that we know what it is. It's not some sort of unspecified constant. Okay, this is a number we can evaluate. And now the main result is that when we apply this algorithm to data with noisy labels, as long as we know the transition metrics between the noisy labels and the true labels, this algorithm will give us valid coverage, at least the 1 minus alpha. Now, this is already nice because there's no assumption here about the machine learning model being reasonably accurate. No, we don't need that. We just need to know the transition metrics between the noisy labels and the true labels, and then we get guaranteed 1 minus alpha coverage. So if there was any problem of possible under coverage with this algorithm, it disappears. And on top of that, if there was any problem of over coverage, it should also go away as long as the sample size is large enough. So we have this upper bound that requires a few additional technical assumptions, but they're relatively mild. And it says that the coverage is going to be smaller than 1 minus alpha plus some positive quantity that I can write explicitly that decays roughly as 1 over square root the sample size. And so here I can show you how it works empirically. This is a numerical experiment where we have a classification problem with 4 possible classes. I'm varying 2 things in the experiment. I'm varying the number of data points used to calibrate the conformal inferences, and I'm varying the amount of labeled noise. So contamination 0 means there's no labeled noise. Contamination 20 roughly means that 20% of your labels are wrong. And so the gray curve here shows the coverage and average size of standard conformal inferences calibrated using the noisy data. What you can see is that they achieve 90% coverage exactly when there's no label contamination, and then they become increasingly conservative when the label contamination becomes more prevalent. And we apply our algorithm, it corrects so first of all, it also has coverage always greater than 90%, but it gives you smaller prediction sets as long as the sample size is large enough. And roughly this this coverage basically decays as 1 over square root n. Now, the main observation from this is that unfortunately, when the sample size is small, this algorithm is giving us even more conservative inferences. And the reason is that it is guaranteeing coverage under milder assumptions, and so that's the price we need to pay. However, what if we don't want to pay this price? We already have some results that tell us that most of the time, standard conformal inference is too conservative anyway, as long as you've trained a reasonably accurate classifier. So can we use that information to try to get the best of both worlds? Ideally, we would like to only improve the size of the prediction sets if we believe that they're already too big to begin with. And so the most intuitive thing you can do is to simply apply both methods and take the smallest prediction set between those given by the 2 options. Okay, so let's be greedy and let's try to do that. And it turns out that we can actually, okay, so how do you write it? You write it like this. This greedy approach is basically equivalent to applying that adaptive method that I described before, with this extra correction. So instead of subtracting delta hat minus the little delta from 1 minus alpha in that set script ik, you truncate that as 0. So this is the way that we study theoretically, but the intuition is you apply both the standard method and the new method and you take the smaller prediction set. This is equivalent. Now, the result that we have is that as long as the true coverage inflation factor is positive, and in fact it needs to be a little larger than positive, it needs to be larger than the small constant, then this greedy approach still has valid coverage. And so that supports doing this greedy approach that basically gives you that red curve that will take the best of both worlds. And so with this approach, this is the approach that we apply if you have reason to believe that your classifier is already reasonably accurate, which is what we almost always observe in practice. And then it will either give you prediction sets that are basically equivalent to the standard ones, or it will make them more informative. And we can also study the, and so this will basically decay. The coverage will also approach 1 minus alpha at the same rate as the original method. Okay, so there are several extensions to this methodology that I didn't have time to present today. One extension is that you may want to construct prediction sets with marginal coverage instead of label conditional coverage. So almost everything I described today translates naturally into the marginal coverage setting, although the notation is a little more complicated. One key difference, though, is that the coverage inflation factor that you get for marginal coverage is different. And it's a little more complicated because it's not just defined as the difference between 2 CDFs. It's written as this weighted sum of differences. And the weights row relate to the marginal frequencies of the true and noisy labels. So row k is the probability that a random data point has true label equal to k, and row tilde k is the probability that a randomly chosen data point has contaminated label equal to k. These two quantities are not necessarily the same. And if you want to study or correct prediction sets with marginal coverage, you need to know these two quantities, or at least their ratio. So that is one key difference. Another extension that we have in the paper, but I didn't want to discuss, is that you can use a modified version of this adaptive algorithm to construct prediction sets that are probably approximately correct. This is PAC. This is an acronym that is used in machine learning literature. What it means is that instead of saying that the coverage on average is going to be 1 minus alpha, you can say that the coverage is going to be greater than 1 minus alpha with high probability, where that probability is taken with respect to the supervised data set that you observed. So this is a much stronger type of coverage, but it can also be achieved, and it also suffers from the same problems when you calibrate using noisy data, and can also be fixed in a very similar way. Now, in terms of, I promised that I would say something about relaxing the assumption that the transition matrix is known. So one way that you can relax it is by putting some kind of parametric model in it, and then allowing one parameter to be not known exactly. So that's a way of relaxing it while making your life still reasonable. So one way you can relax this is by putting this model on M. So you could say that the transition matrix is equal to the identity matrix rescaled by 1 minus epsilon plus a matrix of ones everywhere rescaled by epsilon over k. So what that means intuitively is that for any new data point with probability 1 minus epsilon, you keep the original label, and with probability epsilon over k, you assign any particular new label, which could also be equal to the old label. So basically 1 minus epsilon is going to be the fraction of roughly, okay, so we can think of epsilon as being roughly the fraction of incorrect labels in the noisy data set. There are some cases where this is just a useful approximation, and there are some cases where this is actually known to be true. For example, in the context of label differential privacy, this is the standard way of adding noise to the data to preserve user privacy. So if you assume that this is known, then all the expressions and algorithms that I showed before become a little bit simpler to visualize. But in particular, the coverage inflation factor or its empirical estimate, they take this nicer form. They don't depend on the matrix V anymore because we know what the matrix V is. They will just depend on epsilon and k through this form. And one extension is that instead of assuming that epsilon is known exactly, you can assume that you have some confidence bound for epsilon. So we have some results where we calibrate the conformal inferences starting only from approximate knowledge of epsilon, where we might have an upper bound, we might have a lower bound, we might have both of them. And so that is one extension that you can read about there. And we also have some thoughts about how you can try to estimate epsilon from the data, which is something that you can do if you have some clean data. If you don't have any clean data, you might need to use some outside prior knowledge to guess what it is. Okay, so this type of simplified model is actually what we used in the real data application. The real data application involves image classification from the famous CIFAR10 dataset. So there's a version of the dataset called CIFAR10H that has imperfect labels assigned by approximately 50 people through the Amazon Mechanical Turk for each image. So now you can think of this data set as having 10,000 images or 10 classes, airplane, car, bird, and so on. And each image has multiple labels, from on average 50 labels. And most of these labels agree all the time. They don't always agree. And for this data set, we also have what is considered to be the true label. Okay, so that would be the label that is in the classical version, the CIFAR10 label. So what we do is that we randomly pick one human assigned label for each image from the 50 that were available. We pretend that is the noisy label, and then we calibrate conformal inference using these noisy labels, and then we also apply our algorithm. And for our algorithm, we assume this simple model that is not actually true in this case, but it's a convenient model. And we use epsilon equal 0.05 using this outside knowledge that these noisy labels are approximately correct 95% of the time. And then we use a pre-trained model to calculate the conformity scores. And this is an example of what some of those prediction sets look like. This is a fairly simple classification task where we have a pretty accurate neural network. So most of the time, both the standard approach and the adaptive approach will give you the correct prediction. Will give you a prediction set that contains only one label. And most of the time, that would be the correct label. But sometimes the algorithm is not sure, and you may sometimes get some prediction sets that are larger. So those are the communicating some uncertainty about the prediction. And long story short, the adaptive algorithm sometimes returns smaller prediction sets, which is nice. And here you basically have that summary. So in this particular figure, I'm reporting the results corresponding to prediction sets designed to obtain 90% marginal coverage. And you can see that the standard approach calibrated with that noisy data that comes from CIFAR 10 is larger than necessary. And using the adaptive approach, you can at some point get pretty close to having all prediction sets with size 1. Not all of them, because the model is not perfect, but it's a very accurate model. So you should at some point be able to get pretty high confidence predictions for most data points. And we also have some results where we calibrate for label conditional coverage. So the decay of the extra coverage for label conditional coverage is a little bit slower because you have to calibrate separately for each class. So it will take a slightly larger sample size before you get to the desired 90% coverage, but you still have some improvement compared to the standard approach. Okay, so with that, I am ready to conclude. I'd be happy to discuss offline later any possible ideas for future work, starting from here. I think some ideas for future work that I thought about are about extending these techniques to deal with other type of measurement errors that you might have in the calibration data used for conformal prediction. For example, one could think about having measurement errors in continuous value data. So to try to extend these techniques for regression instead of classification. A more challenging question would be whether you can do anything like this in the setting of more complicated conformal inference approaches that don't use data splitting, but use some other type of resampling technique, which tend to be more computationally expensive and also difficult to study theoretically, but can be more efficient if you are working with a small data set. And then here's a link to the paper. I should have said it before, but I'm sorry, but this is joint work with Rachel Wang, who's a professor at the University of Sydney in Australia, and Xin Tong, who's a professor in my department. And we also have, okay, we also have some software, and it's pretty basic, but it should be understandable if you want to try this out by yourself online and has some examples on how to use it. I'd be very happy to take any questions. Thank you. Right. So if you have a large data set with clean data, then you should just use that to do your inferences, and you don't need to estimate epsilon. I agree. In fact, I think the most interesting practical cases are those where either you know epsilon from relevant prior knowledge or from because the agent that was releasing the data, for example, the data curator told you what epsilon is. So that is a realistic case. Or if you have some uncertainty about epsilon, I think it is easier to deal with in terms of putting some confidence bounds, again, informed by external knowledge. I think that the tools that we have for estimating epsilon have some interest by themselves and are going to be practically useful only in those situations where you have a very limited amount of clean data. Sometimes conformal calibration can be data intensive, especially if you care about label conditional coverage, because you have to split the data by label, and you might not in the end have that many observations for each particular label. On the other hand, though, if you're willing to believe the simplified model, for example, it only has one parameter to estimate. So you might be able to get a reasonable guess of what epsilon is without having that many data points for each separate class. So that would be useful. For you have enough data to estimate this epsilon parameter, enough clean data, but you don't have enough clean data to do separate label conditional calibration for each class. That would be my example. Of course, if you just have an abundance of clean data, then there's no problem.
Yeah, so I love your talk. So I'm wondering if it's a simple extension or a more difficult extension than some misclassification of labels are worse than others. I have a image that has different views of dogs. Maybe if I mislabel the breed of dog, it's a big deal here, but certainly I don't want the dog to be misclassified as a
Yes.
dog.
Yeah, that's
So
yes.
Is that a simple extension, or is that one that requires a lot more nuance that can be possible?
So I think that would, first of all, I think that would be a very interesting extension. I don't think it would be super difficult because there is already relevant work on how to quantify and control classification errors when you have this type of structure in the labels. So I don't think anyone has looked at the specific problem you're mentioning, probably largely because this work is very recent. But they have looked at situations where you're not interested in label noise, but you are interested in making classification for this hierarchical or structure type of label. And so I think one would need to take that work and combine it with this. If you want to be the one to do it, I will say don't wait too long.